Hello everyone. Here's today's differential equations problem. The question is as follows. Consider the differential equation dx over dt is equal to x times e to the power of minus ax minus x squared. Now here, a is the bifurcation parameter, and the question is asking us to sketch a bifurcation diagram as well as indicate the stability of each section created by the bifurcation diagram, and then additionally to identify any thresholds where a change in long-term behavior occurs. Now, the first step to solving our differential equation that we've been given is to simplify it. In order to sketch the bifurcation diagram for this equation, you would first have to plot the equilibrium solutions as a function of the parameter a. The equilibrium solutions, however, can be found by setting dx over dt equal to 0 and then simply solving for x. The first step in doing this is taking our original equation, x times e to the power of negative ax minus x squared, and setting it equal to 0. After this, we can simply simplify it, and we would get x times the quantity of e to the power of negative ax minus x equal to 0.
Okay, so now that we have simplified our differential equation, we get this. And the next step that we must perform in order to plot the bifurcation diagram is to find the equilibrium solutions of this differential equation. Now, in this case, there are two equilibrium solutions. The first one is a bit obvious, that being x equals 0. Now, x equals 0 is an equilibrium solution regardless of what value of a you have. But in order to find the second equilibrium, you need to solve the equation e to the power of negative ax minus x set equal to 0. Now this is to find the other equilibrium solution, and we'll find it in terms of a. So we want to isolate a in this equation and get it equal to something. So in order to do that, the first step would be to add x to both sides of our equation. That way we get e to the power of minus ax set equal to x. Once we have this, there's only one way to get rid of our e and to bring down our negative ax from the exponent. And that would be to multiply both sides by the natural log. And once we do that, that gets rid of this, and we're left with minus ax set equal to the natural log of x. Once we have minus ax equal to the natural log of x, the only way that we can get this a to be by itself is by dividing both sides by an x. So that leaves us with a minus a equal to the natural log of x over x. And then in order to get a by itself, simply we would just take a and make it equal to the natural log of x, the negative natural log of x over x. And that is our second equilibrium solution. And one thing to note is that this equation cannot be solved analytically, and the only way to do it is to use numerical methods or graphing in order to find the roots. In this example here, we can plot the function f of x is equal to e to the power of negative ax minus x, and find where it crosses the x-axis.
Now, the next thing to do once we have found our equilibrium solutions is to graph them. Now, as you can see from the graph to the right, there is a root near x is equal to 0.7 for a value of a is equal to 1. Now this root moves towards 0 as it increases, and it follows this trajectory here. Therefore, we can see that there is a second equilibrium for values greater than some critical values on our graph.
Okay, so now that we have rearranged our second equilibrium solution, e to the negative ax minus x equals 0, we found that a is equal to the negative natural log of x divided by x. Now the next step that we can do in order to plot our bifurcation diagram is to take this equation, a is equal to the negative natural log of x divided by x, and plug in different values of x and solve for values of a. That will allow us to get two sets of points, and I guess even more, that you could use in order to plot the bifurcation diagram at various points on our graph. So let's do that for a few here. So say that we have a value of x is equal to 1. For x is equal to 1 up here, we get a is equal to the negative natural log of 1 divided by 1. Now this value is quite an easy one to solve for. It's just 0. So our first value, let's set up a table here. So an x and an a table. So for x is equal to 1, we get a is 0. Now the next thing we can do is we can have x is equal to 2. Now for x equals 2, we get the same thing. A is equal to the negative natural log of 2 divided by 2. And this is approximately equal to negative 0.347. So as we can see, we're gradually going down here. So we have a value of x is equal to 2, and we have negative 0.347. Now for x is equal to 3. For x is equal to 3, we have the negative natural log of 3 divided by 3, and this is equal to approximately 0.366. All right, so for x is equal to 3, we find that a is equal to negative 0.366. All right, so what about for 4 and for 5? X is equal to 4 and 5. Well, for x is equal to 4, we find that it is equal to the same value we get when we had x is equal to 4, which is 0.347. Odd. So that means that this value here is a point where a change in the behavior occurs, which is what our problem wanted us to find, was any changes in the equation that would give the behavior long time and make it different. For x is equal to 5 now, for x is equal to 5, we have the negative natural log of 5 over 5, and that is equal to negative 0.322. All right, so now we're starting to go more positive here. So we see here, whereas here we were going more negative, starting from where x is equal to 3, we're going to end up with our values of a becoming more positive. Okay, so now that we've plotted our bifurcation diagram, we have 3 unique areas here that we need to figure out whether or not they're positive or negative areas. And we do this with area 1 being to the left of our first equilibrium solution, x is equal to 0. And then we do our second one is above the line e to the power of negative ax minus x equals 0. And then below that line is number 3, and those are the 3 areas that we'll need to look at.
So now that we have plotted our bifurcation diagram, we have 3 areas here labeled 1, 2, and 3 on our bifurcation diagram, which is plotted to the right. And these areas, now we have to figure out whether or not they are stable and whether or not they are positive or negative. So area 1 is to the left of the line x equals 0, which was our first equilibrium solution. Now area 2 is above our second equilibrium solution, e to the power of minus a times x minus x equals 0. And then area 3 is below that second equilibrium solution. So for x is less than 0, let's choose a value of, say, x is equal to negative 1. By substituting this into our derivative, dx over dt, we get dx over dt is equal to -1 times e to the power of ae to the power of a minus 1, or minus a -1 squared. And if we simplify this, we get minus e to the power of a minus 1. So then, if a is less than 0, e to the power of a is greater than 1 rather, sorry. So dx over dt is negative for x is less than 0, which also means that x equals 0 is a fixed point and is stable. If a is greater than 0, then e to the power of a is less than 1, so dx over dt, our derivative, is negative for x is less than 0. And this means that the x equals 0 is a fixed point, stable solution. Alright, so for x is greater than 1 over a, our second area here, let's choose an x value of, say, x is equal to 2 over a. By substituting this into dx over dt, our derivative, we get dx over dt is equal to 2 over a times e to the power of -2 minus 4 over a squared. Now here, since e to the power of -2 is very small, we get our derivative dx over dt, we find that it is negative for x is greater than 1 over a, which means that this point, x is equal to 1 over a, is a fixed point, but it's unstable. Finally, for x is greater than 0, but it's also less than 1 over a, so it's in between our two areas there, let's choose 1 over 2a to be our x value here. By substituting this into our derivative dx over dt, we get dx over dt is equal to 1 over 2a times e to the power of -1/2 minus 1 over 4a squared. Now, since e to the power of -1/2 is positive, and 1 over 4a squared is also positive, we find that our derivative dx over dt is also positive for x is greater than 0 and less than 1 over a. Now this means that the x equals 0 fixed point is unstable here, but the x equals 1 over a fixed point is stable. So now that we've gotten our three areas here, let's summarize it. So by summarizing our results, we could summarize the signs of dx over dt, our derivative, in each section as follows. For x is less than 0, our derivative dx over dt is less than 0, and the x equals 0 fixed point is stable. For x is greater than 0 but less than 1 over a, our derivative dx over dt is greater than 0, and the x equals 1 over a is a fixed point and is stable. For x is greater than 1a, however, dx over dt is less than 0, and the x equals 1a fixed point is unstable here. The only one that is unstable is that second area. Now, one quick thing that we can note here is that the equilibrium solution at x equals 0 will always be stable no matter what conditions you submit this to, but the stability of the equilibrium solution at x equals 1 over a can change at a equals 0. Now this is where bifurcation occurs in our bifurcation diagram for this equation. For a is less than 0, we find that x equals 0 fixed point is stable, and for a is greater than 0, we find that the x equals 1 over a fixed point is also stable. I'd like to thank all of you for watching this video, and I hope you learned something of value today, and I hope you can contribute it to something in the future, and hopefully you can use it to plot your bifurcation diagrams more easily in the future.